Hello everyone, this is Jesse Crawford with New York Medical College, and this is the supplemental lecture for estimation. This lecture is about estimation. More specifically, we're going to discuss how you can take a sample from a population and then calculate certain numbers in that sample, like the sample mean, in order to estimate certain numbers about the population, like the population mean. So to get us started, let's go ahead and take a look at this first example where we have a normal distribution, and this normal distribution corresponds to the population of all men's weights in New York. Now, in this example, we know that the population mean is 180 and the standard deviation is 30. So again, those are population parameters. So that 180 represents the average weight of all men in the population, and the sigma equals 30 represents the standard deviation of all men in the population. Now, normally we aren't able to obtain these numbers directly because we can't actually measure everyone's weight in the population. It's just too expensive. So instead, we're going to take a sample. So how do we actually get a sample? We're going to randomly select one person from the population and measure that man's weight, and we'll get a number when we do that. We're going to call that number x1. Then we'll randomly select a second man and measure his weight, and that will be x2, and so on and so forth. And we'll keep going until we have n observations. So in this situation and throughout this course, lowercase n is going to represent the sample size. So if we randomly selected 2,000 people for this sample, n would be equal to 2,000. So anyway, a sample basically is a list of numbers x1, x2, x3, all the way up to xn. And we've already talked about how once we have a sample, we can calculate the sample mean, which is just going to be the sum of all the numbers in our sample divided by n. And we can calculate the sample standard deviation. We looked at that in lecture 2. Well, it seems pretty reasonable that if we are trying to estimate the population mean, then we could just use the sample mean to estimate it. And the same thing goes for the standard deviation. If we didn't know the standard deviation and we wanted to estimate it, we could use the sample standard deviation. So this is common sense, but it actually turns out that this is the mathematically correct thing to do. So again, in this example, we know that mu is 180 and sigma is 30, but that's not very realistic. In a more realistic example, we don't know the population mean. We don't know the population standard deviation. And so in order to estimate those, we're going to take a sample, we'll calculate the sample mean and use that as our estimate for the population mean, and we'll calculate the sample standard deviation and use that as our estimate for the population standard deviation. Here's an example that shows that in action. Let's say we took a sample of size 2,000 from our population, and we got a sample, which it's just going to be a list of 2,000 numbers. We might get 165.36 pounds for the first person that we randomly select. We might get 223.15 pounds for the second person we select, and so on and so forth. Once we get that list of 2,000 numbers, we're going to take the sample mean of all those numbers, and in this case we get 179.63. I actually generated 2,000 numbers on a computer in order to do this example. And the sample standard deviation is 30.68. So our estimate for the population mean would be 179.63, and our estimate for the population standard deviation would be 30.68. There's a couple of things that are worth pointing out here. First of all, notice that the sample mean is very, very close to the population mean. That's basically happening because we have such a large sample size, and we'll get to that later. The same thing can be said for the sample standard deviation here. It's very close to the population standard deviation. But I also want to point out that if you look at the numbers in the sample, there's a lot of variability there. The first number is 165.36. The second number is 223.15, and so on. These numbers are not really close to 180, and the reason for that is the standard deviation is 30. And we saw last time that when you're dealing with normally distributed data, about 95% of the observations are within 2 standard deviations of the mean. So 2 standard deviations here is 60. 180 minus 60 is 120. 180 plus 60 is 240. So that means that we're going to get observations anywhere between 120 and 240 95% of the time. So there is a lot of variability in the numbers that we can observe in our sample. Okay, so we've talked about how if we have a population, we can take a random sample from that population and then calculate the sample mean and use that as an estimate for the population mean. Now we're going to talk about the idea that we could actually do that over and over again. So I could take a random sample of size 2000, calculate that sample mean, and write that number down. And then I could do that again tomorrow. I could take a new sample of size 2000, write that number down. Then I could do that the next day and the next day. Well, I actually did this using the computer that I was using to generate this data. I took a random sample of size 2000 from the population and I calculated the sample mean and I got 179.63. Then I took another sample of size 2000 and I did the same thing, but this time I got 179.12, and then I kept repeating this process a few more times. So by doing this, we see a few interesting things. First of all, we see that the sample mean x bar is actually a random variable, and this makes perfect sense. If I take a random sample of size 2000 from my population, well, the min that I actually select in the sample were randomly selected, which means that the numbers that I get whenever I measure them are basically random numbers, and so the sample mean I get is going to be random. To think about this a different way, if I take one sample today and I calculate the sample mean and I get 179.63, well, when I take a sample tomorrow, there's no reason to expect that I'm going to get the same group of people. I'm probably going to get a totally different group of people, and so the sample mean that I get is going to be totally different. And you can see that that's what actually happened in this example. So the sample mean is a random variable. It's not always going to be the same number. It's going to change depending on which sample you select. Now, another thing that you can see is that on average, the sample mean will be equal to the population mean. So you can see here that sometimes when I calculate the sample mean, I get a number that's a little bit under 180, but sometimes it's a little bit over 180. But the point is, if we continued this process forever, and we wrote down a number every day for forever, then the average of all those sample means that we get would actually be exactly equal to 180. So, and again, on average, the sample mean is equal to the population mean. And that's really good because we want to use the sample mean to estimate the population mean. And so it would be really bad if the sample mean were systematically bigger or systematically lower than the population mean. But that's not the case. The sample mean is sometimes above the population mean and it's sometimes below the population mean, but on average it's equal to the population mean, and that's what we want to happen. Another observation that we can make here is that the variability in x bar is very small. So on the last slide we saw that whenever we take a sample from the population, we can get numbers anywhere from 120 to 240. We could even get numbers that are more extreme than those. So there's a lot of variability in the numbers that we can get. But what this example is showing is that if your sample size is really large, then your sample mean will be very close to the population mean. There will not be a lot of variability. And again, that's a good thing because, again, we're trying to use the sample mean as an estimate for the population mean. Okay, let's take a look at that last statement, the variability of x bar is small. And let's analyze that in a little more detail. Now, the sample mean x bar is a random variable. And every random variable has a standard deviation. The standard deviation of a random variable is the number that measures how much variability that random variable has. And we actually have a special name for the standard deviation of the sample mean. We call it the standard error. And the abbreviation for that is SE. And the symbol that we use for it is sigma sub x bar. So we have SE, which is the standard error, equals sigma sub x bar here. Now it turns out we have a nice formula to calculate this. It's equal to sigma divided by the square root of n. In other words, it's the population standard deviation, which is 30, divided by the square root of the sample size. So we're doing 30 divided by the square root of 2000, and we're getting 0.671. Now you may be wondering, why is this SE number coming into play in this example? On the previous slide, we said that the standard deviation is 30, so why isn't the standard deviation of x bar 30? Well, there's really two standard deviations here. 30 is the population standard deviation. It represents how much variability there is if I look at all the people in the population. So there's a lot of variability there. If I look at a list of all the weights of all the men in New York, I'm going to get a wide range of values. Some people are going to weigh only like 100 pounds. Some people are going to weigh over 300 pounds. There's going to be a ton of variation there. But that's not what this number SE represents. It doesn't represent the variation in the population. It represents the variability of X bar. In other words, if I calculate the sample mean today and I write that number down, and then I do that tomorrow, I take a new sample and I write that sample mean down, and I continue that process. From what we've seen, when you do that, you don't get a lot of variability. The numbers you get are always going to be very close to 180, especially if your sample size is high. So there is a lot of variability in the population, but if you take a large sample and you calculate the sample mean, and you repeat that process over and over, there will not be a lot of variability in the sample means that you get. Now, we've already talked about the fact that X bar is a random variable, and anytime you're dealing with a random variable, you always want to ask yourself the question, what kind of distribution does this random variable have? For instance, does it have a binomial distribution or a normal distribution, or there's a lot of other distributions we haven't talked about, things like uniform distributions and Poisson distributions. What kind of distribution does it have? And there's this really nice theorem called the central limit theorem that says as long as your sample size is at least 100, the sample mean will have approximately a normal distribution. So let's look at what this says. It says X bar is approximately normal, and then it has the number mu and sigma sub X bar squared. So what is this talking about? Okay, well, the sample mean has an approximately normal distribution. Now, whenever you're dealing with a normal distribution, you need to say, what is the mean of that normal distribution, and what is the variance of that normal distribution? Now, you might say, well, the mean is 180 and the standard deviation is 30. That's what it says in our population. But again, those aren't the right numbers to look at. Those numbers represent what's going on in the population. What we want to know is if I keep finding sample means repeatedly, and I'm looking at those numbers, what is the mean of those numbers and what is the standard deviation of those numbers? But we've actually already said what those are. We've already said that on average the sample means are equal to the population mean. So the mean of X bar is actually just going to be 180 here. So that's nice. We don't have two different types of means. What about the standard deviation? Well, again, we've actually also already said what the standard deviation of X bar is. It's this number SE, which is sigma sub X bar, and we calculated it to be 0.671. So if the standard deviation of X bar is sigma sub X bar, then the variance of X bar is sigma sub X bar squared. And so that's why this equation says X bar is approximately normal with mean mu and variance sigma sub X bar squared. So for this particular example, X bar is approximately normal with mean 180 and standard deviation 0.671. And we'll be able to use this in order to actually calculate some probabilities, as we'll see on the next slide. Okay, now that we've sort of discussed the theoretical framework that we're going to be working in, let's take a look at a practical problem. So this problem says that men's weights in New York are normally distributed with mean 180 pounds and standard deviation 30 pounds. So it's just the scenario that we're looking at on the previous slides. In a random sample of size 2000, first of all, find the standard error of the mean, and second of all, find the probability that the sample mean is between 178 and 182. So the first thing we're going to do here is find the standard error of the mean, and we already did that on the previous slide. The standard error is the number SE. It's the same thing as sigma sub X bar. The formula for that is sigma divided by the square root of n. So we take the standard deviation of 30, divide by the square root of 2000, and we get 0.671. Alright, well, let's go ahead and calculate the probability that the sample mean is between 178 and 182. Well, from the previous slide we saw that the sample mean is going to be approximately normal, and the mean is going to be the same thing as the population mean, 180, and the standard deviation is going to be the standard error that we calculated, 0.671. Now we're trying to calculate the probability that X bar is between 178 and 182, so the next line that we write down is just writing that out in a mathematical notation. It says probability 178 is less than or equal to x bar is less than or equal to 182. So we've simply written down the probability that we want to calculate. How are we going to calculate this probability? Well, we're dealing with a normal random variable, and we saw in the last chapter that in order to calculate this type of probability, we're going to use the z-score approach. So we're going to take each thing in that inequality, we're going to subtract the mean, which is 180, and we're going to divide by the standard deviation. But we're dividing by the standard deviation of x bar because we're calculating a probability that involves x bar. So we're going to use 0.671, not 30. So we go ahead and do that. And we can calculate these two fractions on the ends, and we get negative 2.98 and we get positive 2.98. As we saw before, when we do this to the random variable, it's going to turn into a standard normal random variable z. So we're basically calculating the area between negative 2.98 and 2.98 under the standard normal curve. And we saw how to do that before. We're going to look 2.9 up in our table and get 0.9986. Then we're going to look up negative 2.98 and get 0.0014. And we're going to subtract those two numbers and get 0.9972. So what this means is that if you kept taking samples of size 2000 and writing down the sample mean and doing that every day for forever, then 99.72% of the time, the sample mean that you get would be between 178 and 182. And that's actually really quite remarkable, because that means that if we're going to use the sample mean as an estimator for the population mean, that our estimate's going to be really close. Our estimate's going to be between 178 and 182, well over 99% of the time. But 178 to 182 is a pretty narrow range. I mean, if you wanted to estimate the average weight of men in New York and you knew that you were going to be within 2 pounds of the right answer with your estimate, you'd be really happy with that, because 2 pounds is not really that big of a weight difference. So if you can estimate the average weight within a couple pounds margin of error, then you're really happy to do that. So this is a very nice result. Okay, so thus far our discussion has focused upon the idea that we know that the population mean is 180, and we're trying to calculate the probability of certain things happening with the sample mean. But as we discussed earlier, this isn't really the most realistic situation. It's much more realistic to be in a situation where we don't know what the population mean is, and we're trying to estimate it. So that's what we're dealing with here. You can see in the diagram we have a normal distribution, and we know that the standard deviation is 30. So for today we're going to be assuming that we know what the standard deviation is. But it says mu equals question mark. We do not know what the population mean is. So as discussed before, we're going to take a sample, and then we're going to use the sample mean to estimate the population mean. So as an example of this, let's say that we had a sample of size 2000. In other words, n is 2000. And when we take the sample, we get a sample mean of 179.63. Well, then that's going to be our best estimate for the unknown population mean mu. So our estimate for mu would be 179.63. And we call this a point estimate because we're simply trying to estimate where the point mu is. And we're not yet taking into account at all the margin of error for this estimate, but that's what we're about to do. Well, what do I mean by margin of error? Well, we know that our point estimate is not actually the true population mean. We know that our estimate isn't actually 100% correct, because it's just based on a subsample of the population. We're not actually measuring everyone in the population. We're just taking a random sample and taking the mean of that sample. So we know that we're going to be off by a little bit. The question is, can we try to estimate how far we are off by? And this leads to the concept of margin of error. So margin of error is about how far you think your estimate is from the true value. And our abbreviation for margin of error is going to be MOE. So the margin of error is equal to 1.96 times sigma divided by the square root of n. Now, you may be wondering where this 1.96 comes from. And it comes from the fact that 95% of the time, a normal random variable is within 1.96 standard deviations of the mean. For a while now, we keep saying that 95% of the time, a normal random variable will be within 2 standard deviations of the mean. Well, it's really not 2, it's really 1.96. You can also see that below this formula it says the confidence level is 95%. So as we'll see later, if we try to change our confidence that we're going to have in this margin of error, it's actually going to change that 1.96 to a different number. Anyway, the margin of error is 1.96 times sigma divided by the square root of n. Now you'll recognize that sigma divided by the square root of n is actually the formula that we used for standard error on the previous slide. So what this is actually saying is that to get your margin of error, you just take your standard error and you multiply that by 1.96. So to complete the calculation here, we have 1.96 times 30 divided by the square root of 2000, and so we get a margin of error of 1.32. And we have a confidence level associated to this of 95%. So to see what this means, we need to turn to the concept of what a confidence interval is, and we'll see that next. Alright, so you can see that I've rearranged quite a bit of the math on this slide. And let's just take a quick look at what we've done so far. We wanted to estimate the population mean, so we took a sample of size 2000 and we got a sample mean of 179.63. That's our point estimate for the population mean. It's our best guess. Our best guess for what the population mean could be is 179.63. But we know that this estimate is off by some amount. So we calculated a margin of error and we got 1.32 for that. Now, that margin of error has a confidence level associated to it. In other words, we have to say, how confident are we that our guess is really only 1.32 pounds away from the true population mean? And the answer is we're 95% confident in that. So we're 95% confident that our estimate 179.63 is within 1.32 units of the true population mean. So how do we tie all this together? Well, we can use this to form something called a confidence interval, which is basically just a range of values that we think that the population mean might be in. It's an interval of values. The formula that we're using is x bar plus or minus 1.96 times sigma over the square root of n. If we plug 179.63 into that, and we plug 30 in for sigma and 2000 in for n, we get 179.63 plus or minus 1.32. Which basically says that our estimate is 179.63, and we're very confident that we're off by at most 1.32. Now, what we can actually do now is we can take 179.63 and subtract 1.32. If we do that, we get 178.31. Then we can take 179.63 and add 1.32, and if we do that, we get 180.95. So the final answer to this entire process is we get a confidence interval from 178.31 to 180.95. And this means we are 95% confident that the true population mean in this situation is between 178.31 pounds and 180.95 pounds. Okay, let's go ahead and try to talk about what we've done from a practical perspective. We started off with a population of men's weights, and we did not know what the population mean was. We don't know what the average weight of the men in New York is. We do know that the population standard deviation is equal to 30, though. So in order to try to estimate the population mean, we took a sample. We got a sample mean of 179.63, and we also did some mathematical calculations, and we got a margin of error of 1.32. The final result was we got a confidence interval for the population mean from 178.31 to 180.95. The interpretation of this is we are 95% confident that the population mean is somewhere between 178.31 and 180.95. So we don't know what the population mean is, and we're never going to know what that is. All we can do is we can get a confidence interval for it. We can get a range of possible values. So if someone asks us, based on the data that you collected, what do you think the population mean is? We would just say, well, we don't know what it is, but we're 95% sure that it's between 178.31 pounds and 180.95 pounds. And that's really good because we have an estimate that's within about 2 pounds of the true value. So we've got a very accurate estimate here. On the previous slide, we were using the number 1.96 in the formula. And I mentioned that this is not always the number that we're going to use in that part of the formula. And this slide shows what we're going to do in general. So here we have the formula to find the confidence interval for a population mean mu. You see the formula is x bar plus or minus z sub alpha over 2 sigma divided by the square root of n. So what does z sub alpha over 2 mean? Well, before we can say what z sub alpha over 2 means, we need to say what alpha means. Alpha is equal to 1 minus your confidence level. So for example, if our confidence level is 95%, as it was on the previous slide, then alpha is going to be 1 minus 0.95, which is 0.05. Then we can calculate alpha over 2, which is 0.05 divided by 2, and that's 0.025. If you take a look at the diagram, it shows that you have two tails, and in each tail you have an area of 0.025. And that means that the area of that center region is 95%, which is our confidence level. What we really care about is where is that breaking point located that separates that middle 95% from that tail that has 2.5% in it. Well, that point is called z sub alpha over 2. And in this example, it's equal to 1.96. And that's why we're using the number 1.96 in the formula on the previous slide. Now in practice, it's going to be really easy for you to find these z sub alpha over 2 numbers because you just have the table that you can see in front of you to do that. So if you wanted to find z sub alpha over 2 when your confidence level is 95%, you would just look up 95% in the middle column, and you can see that the z sub alpha over 2 value is 1.96. Now I realize that the table is using the notation z sub 1 minus alpha over 2. This is another good example of how certain statistics books do things slightly differently. They use slightly different notation. I prefer to just use the notation z sub alpha over 2 because it's a little simpler and it's more compact. So that's what I'm going to do. It's not going to get us into any trouble this semester because we're only going to need one thing. In other words, anytime you see a z sub alpha over 2 or 1 minus alpha over 2, it's always going to mean the same thing. So you're not going to have to worry about that. So as another example of how to use this table, if your confidence level is 99%, then z sub alpha over 2 would be 2.58. And these are really the two most important values, 95% confidence and 99% confidence. All right, this slide provides us with a completely new example of calculating a confidence interval. So let's say that the average height of women in New York is unknown, but it is known that the standard deviation is 2 inches. Let's go ahead and take a random sample of 500 women, and let's say the sample mean within that sample is 65.32 inches. The problem says find a 99% confidence interval for the average height of women in New York. So to start this problem off, we're going to use our confidence interval formula, and you can see that that's given here, x bar plus or minus z sub alpha over 2 times sigma over the square root of n. You're going to need to know that formula in order to calculate confidence intervals. At this point, we're basically just going to plug numbers in. We know that x bar is 65.32, so we're going to plug that in. In order to find z sub alpha over 2, we just use the table on the previous slide. Since our confidence is 99%, we get 2.58 for that. We're going to just plug in 2 for sigma, since that's the standard deviation, and our sample size is 500, so we're going to plug that in for n. What I would recommend doing is just completely calculate the margin of error first. So wait before you deal with a plus or minus until later. So when we do that calculation, we get 0.23. That's our margin of error. So our confidence interval is 65.32 plus or minus 0.23. But if we want to actually write that as an interval, we need to do 65.32 minus 0.23, which is 65.09. And then we would add those two numbers together and we get 65.55. So the answer here is our confidence interval for women's heights in New York is an interval from 65.09 to 65.55. And the interpretation of this is we are 99% confident that the average height of women in New York is somewhere between 65.09 and 65.55 inches. Now that we've calculated a confidence interval, it's a pretty good time to discuss some of the terminology that is used with respect to confidence intervals. So if we take the confidence interval from the previous slide and write it down, it was 65.32 plus or minus 0.23. And we've already discussed these two terms, point estimate and margin of error. So our point estimate is just whatever our sample mean is, 65.32. And the margin of error is the amount that we think we might be off by. And We calculate that with z sub alpha over 2 times sigma over the square root of n. Once we actually subtract the margin of error and add it to the point estimate to get a confidence interval, the small number we get is the lower confidence limit. And it's called that because this is the lowest that we think that the population mean could be. And then 65.55 here would be the upper confidence interval limit because it's the highest that we think it could be. Now, we're not 100% confident that the population mean is in this range. We're only 99% confident in this example. But that's a pretty high level of confidence. One last thing that we can calculate is the confidence interval length, which is literally the length of the interval. So it's the distance from the lower confidence limit to the upper confidence limit. And of course, in order to calculate that, you're just going to subtract those two numbers and get 0.46. It's worth pointing out that the confidence interval length is always going to be twice the margin of error. So our margin of error here is 0.23, and if you double that, you get 0.46. This slide shows the relationship between the sample size, the standard error, and confidence intervals. Higher sample sizes are going to lead to smaller standard errors. And we actually want smaller standard errors because those are going to lead to smaller margin of errors, and those are going to lead to more accurate confidence intervals. By the same token, smaller sample sizes lead to larger standard errors, which are bad because those lead to large margin of errors, which leads to not very accurate confidence intervals. So to investigate this further, let's go ahead and continue our previous example where the population standard deviation for women's heights was 2 inches. And let's assume that we're going to have a sample mean of 65.32. Now in the left column, we're just repeating the results from the last example. We had a sample size of 500. And you can see that this leads to smaller standard errors because that 500 is in the denominator. The bigger the denominator is, the smaller the standard error is going to be. So we get a standard error of only 0.0894. So how does this lead to a confidence interval? Well, as mentioned earlier, another way to think of the margin of error is it's just z sub alpha over 2 times your standard error. So in this problem, we want a 99% confidence level. So our z sub alpha over 2 is 2.58. So if we just take 2.58 times 0.0894, we get 0.23, and that's our margin of error. This is what we did in the last example. And we get a confidence interval from 65.09 to 65.55. So again, this is just what we did in the last example. Now let's just imagine that instead we had a sample size of only 100, but we still have a sample mean of 65.32. Well, now our standard error is going to be 2 divided by the square root of 100, and so we're going to get 0.2. Notice that this is quite a bit bigger than the standard error we got on the left. And that's going to lead to a higher margin of error because if we take 0.2 times 2.58, we get 0.52, which again is bigger than the result we got on the left. Now look at what happens when we actually form a confidence interval. Well, we get a confidence interval from 64.8 to 65.84. And just think a little bit about which one of these confidence intervals is more useful. It's the one on the left, right? Because the one on the left provides a more precise range for what the population mean has to be. The one on the left says we're 99% confident that the population mean for women's heights is somewhere between 65.09 inches and 65.55 inches. There's only a confidence interval length there of about 0.46. But the one on the right says it could be anywhere from 64.8 to 65.84. We don't have as good of an estimate on the right as we do on the left. We're going to have a bigger margin of error on the right. We're going to have a bigger confidence interval length. So to make a long story short, you're going to want higher sample sizes because they're going to lead to smaller standard errors and in turn smaller margin of errors. But the problem is larger samples are more expensive. So you always have to give up something. You're either going to have to give up resources to get a larger sample size, or you're going to have to settle for a small sample size, which is going to make your estimates less accurate. This slide just talks a little bit about the difference between the term parameter and the term statistic. A parameter is a number that's related to the population. So examples of parameters are population mean, population standard deviation. A statistic is a number that's related to the sample. So examples of statistics are sample mean and sample standard deviation. If you're trying to figure out whether something is a parameter or a statistic, you basically just need to ask yourself, did I use every single number in the population to calculate this? If so, it's a parameter. If you only used numbers from a sample to calculate it, it's a statistic. Another concept that can be kind of confusing related to confidence intervals is the idea of normality. Sometimes people are thinking, if you have a large sample size, then your population is probably going to be normally distributed. This just isn't true. A population may or may not be normally distributed, and we really can't tell unless someone tells us that it's normally distributed, or if we collect data ourselves in order to figure out if it's normally distributed. On the other hand, as long as your sample size is large, then your sample mean will be approximately normal by the central limit theorem, even if your population is not normal. So just to summarize again, a population may or may not be normally distributed, and you really need additional information to know whether it is or not. But as long as your sample size is greater than or equal to 100, your sample mean will be approximately normally distributed. So let's look at this problem real quick. It says, consider the population of all incomes in New York. The first question says, is the population normally distributed? And the most correct answer is, we don't know. We don't have enough information to answer that question. But actually, if you have a little bit of experience with the way incomes are distributed, you would say that the answer is no. Incomes tend to be skewed to the right. They're not normally distributed. So the answer is that they're probably not normally distributed. Now, in the second part, it says, what if we take a sample of size 400? Would the sample mean be normally distributed? The answer is yes, because of the central limit theorem. So even if a population is not normally distributed, the sample mean will be, as long as the sample size is sufficiently large. All right, for the rest of the lecture, we're going to turn our attention to the binomial distribution. This problem says, suppose 10% of New Yorkers are left-handed, and consider a sample of 500 New Yorkers. The first question is, how many are expected to be left-handed? And the second question says, find the standard deviation of the number of people in the sample who are left-handed. Now, this is a binomial problem because we're dealing with a sequence of trials. That is, we're looking at 500 people. And on each trial, there's only two possible outcomes. The person is either left-handed or they're not left-handed. Another word for this is it's a dichotomous problem because there's a dichotomy. Each person is either left-handed or right-handed. The previous problems in this lecture were not binomial problems because we were talking about the weight of a person or the height of a person. In those situations, you're not dealing with only two possible outcomes. There's a whole bunch of possible outcomes. All right, so how are we going to deal with this? Well, whenever you're dealing with a binomial problem, your very first goal should be to figure out what n and p are. N is the number of trials, which is 500 in this problem, and p is the probability of the characteristic that you're interested in. So we're interested in left-handedness here. 10% of our population is left-handed, and so p is equal to 10% or 0.1, however you want to look at that. So the first question says, how many are expected to be left-handed? Well, this is just saying what is the expected value or the mean of the number of people in the sample who are left-handed. And we learned a nice formula for this when we were studying the binomial distribution. The mean of a binomial distribution is NP. So we can just write mu equals NP, multiply 500 by 0.1, and we get 50. This makes perfect sense. If 10% of your population is left-handed and you take a sample of size 500, you would expect about 10% of that sample to be left-handed, and 10% of 500 is 50. So this makes perfect sense. Now the second question says, find the standard deviation of the number of people in the sample who are left-handed. In other words, again, the number of people in our sample who are left-handed is a random variable. Sometimes we're going to get a sample that has 41 people that are left-handed. Sometimes it'll be 52. Sometimes it'll be 47. So the number of people in our sample who are left-handed is a random variable. For that reason, it has a standard deviation, or you could call it a standard error if you want to. What's the formula for that? Well, we learned in the binomial chapter that the variance of a binomial random variable is np times 1 minus p. So we're writing sigma squared is equal to np times 1 minus p. Some people like to use the notation Q for 1 minus p. So we could also write this as NPQ. So it's 500 times 0.1 times 1 minus 0.1, which is 0.9, and that's equal to 45. But that's the variance. That's not the standard deviation. So to find the standard deviation, we just take the square root of 45. We get 6.71. Now we're just going to continue this problem. We're still dealing with a population of New Yorkers, and 10% of that population is left-handed. And this question says, in a sample of size 500, find the probability that fewer than 30 people are left-handed. And you can see that we still have our solution for the last part of the problem written down. And the first step of this problem is to simply take the probability that we're being asked to find and write it down. So we're trying to find the probability that the number of people in our sample who are left-handed is less than 30. So we just write probability x is less than 30. Now, if we try to calculate this probability using the mathematical formulas we learned in the binomial section, we're going to have to add up the probability of 0, 1, 2, 3, 4, all the way up to 29. So we would have to do 30 binomial calculations and then add all of those together. So that's just totally impractical. We can't do that. At the same time, our only other method so far to do this has been to use the binomial table. And if you look in the tables, there's just no entry whenever n is 500. There's no table for that, so we're not going to be able to use the tables either. Luckily, we have this nice little theorem that I've highlighted on the upper right part of your screen. It says that if NPQ is greater than 5, then a binomial distribution with parameters n and p is actually approximately a normal distribution with mean NP and variance NPQ. Okay, so let's see if this theorem actually applies to the situation that we're in. Well, you have to wonder about whether NPQ is greater than 5 or not. So if you look back to what we did though, when we calculated NPQ, we got 45. So 45 is definitely bigger than 5, and so we are going to be able to use this theorem on this problem. What does the theorem actually say? We're dealing with a binomial distribution with n equals 500 and p equals 0.1. What this theorem is saying is this is approximately equal to a normal distribution. The mean is np, which is 50, which is what we already calculated for the mean, right? We calculated mu equals np, which is 50. And the variance is npq, which is 45. Again, we've already calculated the variance. The variance was equal to 45 in our calculation before. Now, saying that the variance is 45 is equivalent to saying that the standard deviation is 6.71. This is really great. We've taken a problem which is binomial with parameters 500 and 0.1. It's not very easy to work with. And we've replaced that with a normal distribution whose mean is 50 and whose standard deviation is 6.71. And it's going to be really easy to work with this distribution. Alright, so how do we actually use this theorem to do the calculation that we want to do? We're trying to find the probability that x is less than 30, and we just saw that we can think of the random variable x as a normal random variable with mean 50 and standard deviation 6.71. But how do you calculate probabilities involving normal random variables? Well, use the z-score approach, right? So we're just going to take each thing in that inequality and find the z-score. So we're going to subtract 50 since that's the mean, and we're going to divide by 6.71 since that's the standard deviation. So we'll just take x minus 50 over 6.71 and 30 minus 50 over 6.71. As usual, the random variable part is going to turn into a standard normal random variable z, and the numerical part can be calculated, and we get 0.0014 when we do that. We get negative 2.98 when we do that. So now we just have to find the probability that z is less than negative 2.98, and we do that by just looking negative 2.98 in the standard normal table, and when we do that we get 0.0014, and that's the answer to the problem. Now we're faced with a couple of follow-up questions. The first one says, is the condition NPQ greater than or equal to 5 satisfied? And by the way, I just want to point out there was a typo on the previous slide. The previous slide said NPQ is greater than 5, but that should have said greater than or equal to. So that's what the condition is. So again, anytime you're working with a binomial problem and you want to use this theorem to do the problem, you're going to have to first make sure that NPQ is greater than or equal to 5. If it's not, you just can't use this theorem. So this question is basically just asking us, is this condition really satisfied and can we really do this? And the answer is yes, because we checked what NPQ was. It's 45, and that is greater than or equal to 5, so we're fine on that. The second question says, do you suspect undercoverage for this sample? Now, we have to know what undercoverage means. We're dealing with a population in which 10% of the people are left-handed. And so if we take a sample of size 500, we would expect to get about 50 people in the sample who are left-handed. Now, it's going to happen that you're not going to get exactly 50. Sometimes you're going to get a little less than 50. Sometimes you're going to get a little more than 50. What would happen if we got fewer than 30 people? Would we really just say that, oh, that's probably due to chance and, it's not that big of a deal? Or would we say that this is a pretty significant situation? This is a big problem because we've gotten way fewer people than we expected to get. And the answer is the latter of those. If you got fewer than 30 people, that's way fewer than you should have gotten, because we actually calculated the probability that that happened would only be about 0.0014. It's about 1/10 of 1%, so it's extremely unlikely that if 10% of your population is left-handed and you take a sample of size 500, that you get less than 30 people who are left-handed. That's extremely unlikely. And so for that reason, if you actually did get a sample like this and the characteristic of left-handedness was important to you, you might need to throw this sample back and get a new sample, or you might need to take additional data and increase the size of your sample until this problem is corrected. So undercoverage is just when the number of people in your sample with a certain characteristic is way, way lower than it should have been according to the statistical calculations that you can do. All right, this is the last problem in this lecture, and it deals with finding confidence intervals for dichotomous data. Now, we've already talked about how to find confidence intervals for population means, but that's when we're dealing with continuous random variables like weight or height. And we haven't talked about how to find a confidence interval when we're dealing with only two possible outcomes. In other words, if we're in a binomial situation, or another way to put that is we're in a dichotomous situation. What do? Well, a perfect example of this is if you're trying to look at a politician's approval rating. They don't know what their approval ratings are, and it's important for them to know that, but they, of course, cannot go to every single person in their state or in the nation and ask that person what they think, because of the expense, right? So they use polling. They take a sample, or they get a polling company to take a sample, and the polling company will ask people in the sample what they think of this politician, and then you use that data in order to estimate the politician's approval rating. Let's go ahead and take a look at this example. It says the governor's approval rating is unknown, and in a sample of 1,000 people, 460 people approve of the governor. We've got two questions here. The first one is to estimate the governor's approval rating, and the second one is to find a 95% confidence interval for the governor's approval rating. Okay, let's start with the first question. The first question is just common sense. If you take a sample of size 1,000 and 460 people in that sample approve of this governor, well, then that's 46%, right? In other words, we're going to take 460 and divide by 1,000, and we get 0.46. So our point estimate for the governor's approval rating is 0.46, or 46%. The formula for that is we say that p hat is x over n. So p hat is the estimate for the approval rating. X represents the actual number of people in your sample who approved of this politician. So x in this problem is 460. N is always as the sample size, so that's what n is 1,000 here. And so we have p hat is x over n, which is 460 over 1,000, and that's 0.46. So that is pretty much just common sense. Okay, how do we actually find a 95% confidence interval for the governor's approval rating? Well, in order to do that, we need to find the standard error. And if you think back to the formula for standard error that we're using for population means, it was sigma divided by the square root of n. Now the formula that we have on this slide is the square root of p hat times 1 minus p hat over n. If you think about this a little bit, this is actually the same thing as sigma over the square root of n. Because for a binomial distribution, sigma squared is equal to np times 1 minus p. So if you do a little bit of algebra, it's a little bit complicated, but if you do some algebra, you'll see that this is really just following from the same formula that we use for the population mean. But in any case, this is our standard error, square root of p hat times 1 minus p hat over n. So let's go ahead and plug into that. P hat's 0.46, so we have square root of 0.46 times 0.54 over 1,000. That gives us 0.0158. Now, what do we do with the standard error in order to find a confidence interval? We're going to multiply that by z sub alpha over 2, and that's going to give us our margin of error. Now, in this problem, we want to find a 95% confidence interval, which means that z sub alpha over 2 is going to be 1.96. So the confidence interval is just going to be p hat plus or minus z sub alpha over 2 times that standard error that we just calculated. So we're going to get 0.46 plus or minus 1.96 times 0.0158. We're going to do that multiplication. We get about 0.03. So that means our point estimate for the governor's approval rating is 46%, and we've got a margin of error of about 3 percentage points. You see this kind of thing in the news all the time. It'll say that someone's polling at 46%, and there will be a little asterisk, and then at the bottom of the page, or if you're watching a TV show at the bottom of the screen, it'll say, oh, the margin of error for the study was 3 percentage points. So what does this really mean? It means this governor could have an approval rating that's anywhere between 43% and 49%. And that's the confidence interval that we get for the governor's approval rating. So that concludes this lecture, guys. I hope that it was helpful. And as always, please let me know if you have any questions about any of the material, and I'll be happy to help you guys out. But until next time, thanks for watching.